They show scaling effect in approximate optimization with quantum annealing on two-dimensional Ising spin glass problem instances. All of these results have to do with approximate optimization as opposed to exact optimization. I should mention that. And the available optimization schemes in general within a quantum computing context are 5. And I mentioned them here so that I can highlight where within each of their procedures efficient codings should bring benefit to them. So in quantum annealing, we start with an easy to prepare superposition, the driver Hamiltonian that doesn't commute with the problem Hamiltonian, and then we slowly and continuously interpolate between that driver Hamiltonian and the problem Hamiltonian, which is diagonal in the computational basis. And what's relevant to us here is that the inverse spectral gap, which governs the evolution time needed to optimize within this context, scales monotonically in the number of qubits present. In variational quantum optimization, for example, QAOA, we have a parameterized quantum circuit ansatz, which we apply to a uniform superposition to get a prepared quantum state. And we measure the expectation value of this quantum state against the problem Hamiltonian and perturb these parameters in a continuous measure parameter perturb loop in order to minimize the expectation value. Shallower circuit is beneficial here, speeds up the computation. And the same is true for quantum imaginary time evolution, where we substitute imaginary time for real time within the Schrodinger equation. The result of that being that higher energy states decay quicker than lower energy states. This breaks unitary dynamics, but those unitary dynamics can be recovered if the trajectory is discretized by quadratization and renormalized at every step. And again, shallower circuits are a benefit to this approach. Grover adaptive search takes the Grover search algorithm and adapts it to an optimization context by creating adaptive threshold oracles, which flag those states whose costs are lower than some threshold y. And at the end of the one iteration, we measure in the computational basis, evaluate according to the cost function, and if we get out a state that's lower in energy than the original threshold we started, we re-encode the article with the new threshold and repeat. This inherits the square root speedup inherent to Grover adaptive search, but that speedup can be negated if the oracle construction is complex enough. And decoded quantum interferometry essentially prepares a superposition over all computational basis states where the probability amplitudes are normalized, normalized costs of those computational basis states raised to a polynomial factor. These all differ in their details, sometimes quite dramatically, but they all involve, which is relevant to us, the encoding problem. How do we express our cost functions in terms of a Hamiltonian that we can then optimize over? And ideally, our Hamiltonians are compact, involving few qubits and few interactions between those qubits. And we can't just take any old combinatorial optimization problem and immediately run it on or using those algorithms. The short reason being that both in analog quantum computing and digital quantum computing, qubits are easier to manufacture, control, and theorize about. And the same is true for 2-qubit interactions as opposed to n-qubit. These are easier to manufacture, control, and theorize about. So the encoding problem reduces to us taking cost functions of some form that we want to optimize, and then projecting those to transforming them to quadratic unconstrained binary optimization problems, QUBO problems. Three things naturally emerge within the encoding problem that we should pay attention to. One, we look to limit the Hilbert space induced by the involved qubits as much as possible, the dynamic range of the cost function as much as possible. This has to do with finite precision of hardware. and limit the interaction degree between variables as much as possible, which, if we do manage to accomplish all these things, results in less influence from noise on the quantum trajectories, less quantum resources are used, and ideally you should see faster convergence to optimal or near optimal solutions. And that motivates the rest of the talk, where I'm going to present here some compact encodings of a few different problem structures. First, and this was a part of my doctoral work, I was interested in taking cost function networks within a biomolecular context and running those on quantum computers. So for example, this is a small protein design problem, 3 variables where each of those variables take on 3 choices. This is a toy example. In reality, there's usually hundreds of these variables and hundreds choices per variable, with pre-computed single body energies and pre-computed pairwise interaction energies between them. There were at the time of my beginning this work, 3 encodings of these problems into binary variables. The 2 most prevalent being one-hot encoding and domain wall encoding. For one-hot, if we have D choices at a given variable, we assign to each variable a register of D bits, and then each choice is encoded by a single bit being flipped to 1 and all the others being flipped to 0. The domain wall encoding is similar, but involves 1 less bit, qubit per node. The choice being encoded by where a string of 1s converts to a string of 0s. Both of these encodings are natively quadratic if we start with the pairwise decomposable cost function network, but many of the bit strings induced by these registers are infeasible states, exponentially many versus the computational basis states that we're actually interested in. The other encoding, exact binary encoding, uses the information theoretic minimum number of bits per vertex, where each bit string corresponds to a variable choice. But the result is a higher order binary problem, which, if we're to run it on hardware, we need to quadratize or reduce the degree of. So one-hot and domain wall encodings are interaction degree preserving. Exact binary encodings inflate interaction degree. And when we actually quadratize exact binary encodings, we end up having to use the same number of qubits as a one-hot encoding. So it seems as if we're stuck if we want to use a minimum number of qubits while at the same time reducing interaction degree to pairwise. So the question I asked was, what can we accomplish if I force two things? One, I want to use the minimum number of bits required to represent the solution space. And 2, I want to limit myself to pairwise interactions between bits. In the case of all those encodings mentioned, those are exact encodings in that they take the solution energies of the original cost function network and they preserve them under transformation, but they introduce all of these infeasible states shown in red here. Under those 2 forcings that I mentioned, we can get out a perturbed version of the cost function landscape with bounded approximation error. So we trade exact preservation of the cost function landscape for perturbation to the landscape, while at the same time preserving the number of bits. And we've called this encoding the approximate binary encoding. The basic idea of it is this: if we have D choices at some variable node, we set up a QUBO with log2 of D bits per node over here, force ourselves to a QUBO, and then solve for these coefficients. And we do that on a 1-body and 2-body level. So for example, if we have a variable that has 8 choices, and these are its 1-body energies, we can assign bit strings to each of those variable choices. We have their 1-body energies, and then we have here tabulated the QUBO coefficients that are induced by these bits. So what we have effectively is a system of linear equations that we can then solve these coefficients from to approximate reproduction of these energies. More specifically, what that looks like is this. So we set up a matrix where the left-hand block lists the bit strings that we've assigned to each of our variable choices. The middle block tracks which bits in these bit strings interact by logical AND. And then we have an additional column here of ones, which we then multiply by a constant factor of the QUBO. We have our list of pre-computed one-body energies and our list of QUBO coefficients. And then we just use least squares minimization to figure out these coefficients to minimize the approximation error between Q multiplied by this B vector and the energy vector. The system is overdetermined, so this is why and where approximation error is introduced. But it's bounded by the least squares error, and this is efficiently computable by way of Moore-Penrose or QR block decomposition. The two-node energies we treat similarly using the choice to bit string assignments from before. So they appear in the left two-hand blocks, or left-hand two blocks of the Q matrix. And then this block tracks which bits between these two registers interact by logical AND. Again, we have a column of ones. Again, we have a list of pre-computed energies. And again, we have a list of coefficients that we're solving for. And the same procedure as use minimization of least squares error using inversion of this Q matrix by Moore-Penrose or QR block decomposition. An issue with this encoding is that the approximation error depends on the choice to bit string assignment. And I've shown that the optimal choice to bit string assignment is NP-hard by reduction to quadratic assignment. So to work around that, I developed this enhancement called Boltzmann sorting, where first we order the bit strings in the Q matrix, prioritizing at the top linearly dependent bit strings, and then order energies in the energy vector over here, prioritizing those with a lowest expected energy. Well, that expected energy for a given choice is its one node energy, and then an average over its neighbor's Boltzmann contributions. Computation of each of these expected energies is parallelizable, so it doesn't add too much in the way of computational overhead. And I went further by developing another enhancement, again, which is parallelizable and fairly efficient. It's a nonlinear optimization step to push error to choices with low expectation of featuring the good solutions in particular. And to do that, we can gradient march on a loss function that measures the difference between the actual Boltzmann probability distribution induced by the QUBO and a desired probability distribution induced by the native cost function network. I've included detail here just in case we return to it, but I'm not going to go through it right now. Putting it together, we start with our cost tables of the cost function network. These are pre-computed and they need to be pre-computed even if you're doing classical optimization. So there's no overhead with that step. Then we classically solve n-squared systems of equation, which are each of sides root d squared. That step is parallelizable. And then we get an approximate QUBO that can be quantum optimized. In the lower right hand, I show for a small exhaustively enumerable problem a comparison between the approximate solution energies and the actual solution energies. Ideally, all these would fall right along the diagonal, but given the constraints that I was working with, that's not possible. But what matters in an optimization context is that high actual solution energies remain high energy under the approximation, and low actual energies remain low energy under the approximation. So if we have a tight cone in the bottom left hand, where all other energies remain above, this is a good thing because we've preserved the lower energy band of the solution landscape. To convince myself and convince you all that this actually works, I carried out with Victor Mulligan at Flatiron a benchmarking study on 6,000 protein design problems, where we used both D-Wave's Advantage 2 quantum annealer and 3 different simulated annealers. The first classical simulated annealer is the Rosetta simulated annealer with an adaptive annealing schedule. This was developed specifically for protein design problems, taking into account their structure and chemical potentials. The other two were written in-house. One operates on cross-function networks natively, the other operates on QUBOs, and it has a fixed, typically logarithmic or geometric annealing schedule. The quantum annealer we ran with inhomogeneous driving and 20 microsecond annealing times. And on the left hand here, I'm showing time to diversity, which is the time required to reach, the wall clock time required to reach a solution within 1 kcal per mole of the actual optimum solution versus problem size being the size of the solution space. And this is a fully quantum result here, where we're comparing between existing encodings and the approximate binary. One hot and domain wall, they're the red and the blue here, and they can only solve these problems up to a very mediocre problem size before topping out. The approximate binary QUBO encoding can be solved up to a much larger problem size. The black dots here involve both the Boltzmann enhancement and the nonlinear optimization, and fitting power law curves to the left-hand region of the plot here, the fit scaling exponent reduces by about tenfold from 0.54 in the case of one hot and domain wall encoding to 0.06 in the case of approximate binary. And then comparing to our classical solvers, we took the best from the quantum results, compared it to the classical, and you can see that the quantum curve falls just about exactly on top of the best classical curve, which is the Rosetta simulated annealer with an adaptive annealing schedule. The main takeaways of this work being that approximate binary encoding outperforms one hot and domain wall encoding, at least in this benchmarking set. And quantum annealing, even at this stage, without error correction problem specific embeddings, is competitive with highly optimized simulated annealing, again, on this benchmarking set. The second
question.
Yes.
What is time to diversity?
Time to solution is the time required to reach the optimal solution within a cost function. Time to diversity is kind of a funny term, but it refers to the time required to reach a near optimal solution. So in this case, we were looking at solutions that fell within 1 kcal per mole of the known optimal. So as long as you reach a solution within that energy band, that counts.
What does the error bar? We have a funny little bar there with data pointing bottom.
Yeah, the bottom one isn't shown because it's on a logarithmic axis, and the error bars are standard errors. So under the logarithmic axis, the bottom bar would go down quite far. It's standard error over many problems that fall within a given size class.
Also, this is the variance. This is the sigma of different problems.
Yeah.
Right.
Yeah.
That's wow. Very interesting.
Yeah, the second application, and this is much more recent work, is to graph partitioning problems, where graph partition problems, we define them as having these 4 properties. Each vertex of the graph must be assigned a label from a finite set. There exists a decomposable cost function over each edge of the graph, depending only on whether or not the labels agree or disagree along an edge. The labels are exchangeable, so there's no inherent order or meaning to 0 versus 1 or green versus blue. And the objective is to minimize the number of distinct labels subject to the constraint that we only allow one label assigned per vertex or edge. So some classic graph partitioning problems include minimum K coloring, minimum K cut, community detection, and all their various applications. And these problems have been approached by quantum computers previously, but only in a decision problem context, where the decision problem asks, can I color this graph with some number of colors, instead of asking the optimization version of the question, what is the minimum number of colors I need to color this graph? And primarily, they've been looked at using one-hot encodings, and they've been formulated originally by Lucas in 2014. There's one example of a more qubit efficient version, which uses a binary encoding, but ends up yielding a higher order unconstrained binary optimization problem. So we asked the question, can we encode the minimization or the optimization variant of these problems using as few qubits as possible? So to do that, we started with the binary encoded decision problem variant that I showed on the previous slide, where log2 of the number of vertices or colors per node are assigned to each vertex. And then the product of bitwise XNORs between registers sharing an edge determines bit strings are the same. So this product evaluates to 0 if the bit strings are different, and it evaluates to some positive number if they're the same. But we need a way of minimizing the number of assigned bit strings while preserving coloring. So the idea was that if we assign significance to the bits of each vertex bit string, we can prioritize coloring with low significance bit strings and therefore minimize the number of colors required. So we take that original decision variant Hamiltonian, and we add a simple penalty term on the end here, where we index the bits within a register from least significant to most. And then for all vertices, sum over the bit positions k and penalize by some pk, repeating that step for all bit positions, such that if we ensure that the lowest significant penalty is less than the second lowest significance penalty and so on, this ensures lexicographic ordering, meaning that low significance bit strings are assigned with priority over higher significance bit strings. And we've shown that under lexicographic ordering, the number of assigned bit strings is minimized, subject to certain constraints being satisfied. We need these weights not to just be in an ordered hierarchy, but they have to satisfy the following two conditions. The first here basically says that the lowest significance bit strings must be exhausted before higher significance bit strings are induced. And this one ensures that proper coloring is prioritized versus lexicographic order. The proofs are in this archive paper, and I won't go through them now, but if these two properties are satisfied, then any global minimizer of our Hamiltonian satisfies proper coloring. And among all possible feasible colorings or assignments, the optimal solution is the one that lexicographically minimizes the vector of bit strings. Some benefits and properties of this encoding include that every single bit string corresponds to a feasible solution. There's an exponential qubit reduction versus one-hot encoding. Interaction degree is bounded, even though we do have a product here that's bounded by log2 of the number of vertices of the graph in the worst case, when in reality, for certain applications such as K coloring, we can actually lessen that bound quite significantly in linear time. Depending on the graph structure, quadratization, if we take this HUBO and convert it to a QUBO, often there's less qubits than one-hot QUBOs. The locality of the Hamiltonian is less. And though I've been talking about graph coloring in particular, the method is applicable to all partitioning problems, satisfying the conditions I outlined before, label symmetry and label minimization objectives. We carried out a quantum annealing benchmark of this as well, over 300 graphs from 5 to 50 nodes, 5 to 200 edges. and encoded the K coloring problem in particular using one hot domain wall and our logarithmic or binary encoding, running 1,000 shots at 20 microseconds each on the D wave, and then looked at time to solution and some other statistics. And the time to solution, this here is the time to the optimal coloring, is shown versus the number of nodes in the graph. And the scaling of our encoding is a lot better than one hot domain wall. This is even after quadratization. And the reason for that is that although the average chain lengths required for the logarithmic and one hot encodings are the same, the chain length variance in the logarithmic encoding is a lot lower. Again, this is due to the locality of the Hamiltonian. And even though domain wall encoding achieves lower average chain lengths and lower chain length variance, the penalties required to achieve those conditions earlier are way higher. And so the annealer ends up suffering from finite precision difficulties. And that's the second contribution. This is current work now where I haven't carried out benchmarking, but there's some theory to discuss. And it's again looking at cost function networks from a different and perhaps more principled perspective versus the approximate binary encoding. And the idea here has us start again with the exact binary cost function network encoding. It's from Berwald et al. In 2020, where we take a cost function network, assign each choice of some variable to a distinct bit string, and then we end up with this higher order binary optimization problem here, where the xi's and xj's are indicator functions given by these products, which evaluate to 1 when the bi's here match with the r's, and it's 0 otherwise. And the gammas in front are just these coefficients here, which come from the original cost function network table. So this encoding is great because it does compress each variable into as few bits as possible, but it yields a QUBO of order equal to the cardinalities of the two highest cardinality registers of bits. So the idea was that depending on the problem structure, what we can do is after binary encoding and transforming it into the Ising basis, we can drop Ising monomials of some degree greater than K max, trading down an approximation error for a hardware targetable Hamiltonian. So basically what this is doing is taking a cost function network, encoding it into a binary variable form, taking the Fourier decomposition of that function, and then chopping off higher frequency modes within the Walsh-Hadamard basis. So depending on where you conduct this chopping, it allows a smooth interpolation between exact encoding and native QUBO form, essentially acting as a low pass filter.
What is QUBO? I'm not familiar with QUBO.
Higher order unconstrained binary optimization. So QUBO, but with higher order terms.
Oh, wow.
Yep.
So you can do that.
Yeah.
By using code.
Yeah. Yeah, the Berwald et al. Paper has a nice explanation of how to carry it out. People typically don't use them very much because quadratic interactions are more favorable than higher order interactions if you're running on actual hardware.
But some problems require high optimization, for example.
Yeah. And you can take a higher order binary optimization problem and then add auxiliary variables so you can transform it into a QUBO. So that's what's typically done. But yeah, when you carry out that quadratization, you end up with the same number of qubits as if you were doing a one-hot encoding, say.
Oh, really?
Yeah. So why we work in the Ising basis instead of the 0-1 is that if we're in the 0-1 basis and we chop off some monomial of degree K that monomial actually contributes spectral content at every degree between 0 and k. So we're getting rid of low degree correlations, and these are the ones that we want to preserve, because ultimately we're interested in preserving the coarse Bayesian structure of our cost functions as opposed to the higher frequency nodes. So we convert to Ising before truncating, and then after truncation, this involves an orthogonal projection onto Walsh nodes of degree less than our truncation degree. And ideally, short correlation ruggedness is removed and coarse Bayesians are left intact. This is an example from continuous optimization, just for sake of illustration. If you have a square wave and this is your function that you're trying to optimize, you can get rid of all spectral modes except for the last one. And if you optimize that function, which is just a sine wave, you end up with a solution that falls within the Bayesian that you're actually trying to fall into in the first place. There's a condition that must be satisfied for these Bayesians to be preserved, though, if we carry out this truncation, which is this here. So if the sum of spectral powers below our truncation degree is greater than the sum of spectral powers above the truncation degree, then we can be sure, and there's a proof forthcoming of this on arXiv, we can be sure that we do preserve the coarse Bayesian structure, and the optimal solution, the original function, is left the optimal solution of the truncated function. And this condition is computable in the order, in the number of couplings directly from the Walsh spectrum. So we can expect this to work under that noise-poor condition that I mentioned. This slide here is to show that we don't actually need to, we can just carry out the Walsh-Hadamard transform on the original cost tables themselves before converting to the exact binary representation. So this is just to say that the coefficients of our HUBO end up being the Walsh coefficients of our original cost function. That's true for subsets of variables spanning one register. It's true for subsets of variable spanning two registers, so that our spectrum decomposes additively over our cost tables. And the noise floor condition on the exact binary encoding is then equal to the noise floor in aggregate across the cost table spectra. And only when our underlying cost function tables are smooth in some sense can we expect there to be spectral decay. So high power in low degree modes, low power in high degree modes. So when the kth order discrete derivative, the finite difference, Lipschitz constant, scales as order of C to k, where C is less than 1, then the spectral power above some truncation degree decays superpolynomially. And some favorable CFN structures that satisfy that condition are smooth physical potentials that have been assigned to bit strings using a gray code. So the ones that I'm interested in are computational biology potentials, Leonard-Jones, Coulomb, hydrogen bonding, solvation terms, low rank pairwise tables, sparse interaction graphs. Unfavorable CFN structures that don't meet this condition, at least in expectation, are random or structuralist tables. Our constraint costs, like KSAT, for example. And even if we do have a smooth physical potential, but we don't assign our bit strings in quite the right way, even a smooth potential can be scrambled so that the spectrum may end up with flat. So like in the approximate binary encoding, choice of assignment of bit string to choice is part of the encoding. Again, I haven't carried out benchmarking on this, but I'm looking to do it again using the same benchmarking set as the approximate binary encoding, and run on the D-Wave, and maybe for some smaller problem instances, QAOA or quantum imaginary time evolution. And the compilation pipeline in full looks like this. We have cost function network, encode as an exact binary HUBO, convert to the Ising basis, and then compute the spectral profile, check satisfaction of the noise port condition, and truncate at some k max where that condition is satisfied. And if it happens to be larger than 2, we can truncate at that K-max, whatever it is, and then quadratize. So even though we're not using the information theoretic minimum number of bits or qubits, we can still reduce the number and then solve on hardware. Yeah, the idea is that we're taking a more rugged cost function landscape and smoothing it while still preserving the global basins. I stole this figure from somewhere else just for sake of representation. That's the truncated binary encoding, and taken together with the other previous results, the approximate binary encoding is effective for quantum optimization of certain cost function networks. The protein design problem in particular is the one that we benchmarked. The logarithmic graph partitioning encoding improves time to solution versus traditional one-hot and domain wall. And the truncated binary encoding might be effective for quantum optimization of certain CFMs, and benchmarking on that front still remains to be done. One more thing actually on this slide. And again, the reason for looking into this problem is that by encoding things compactly in terms of number of qubits and number of interactions, we reduce the Hilbert space that we're operating on. We can usually compress the dynamic range of the class functions that we're working with, and we can reduce the circuit depth if we're running a quantum optimization algorithm on a gate-based computer or the embedding overhead we're running on analog hardware. And yeah, that's it. Thanks for funding some of this research, Quantum VC, and all these other people and organizations.
Any questions online or in the room? Go ahead.
So you showed a lot of 1.8.
Yeah.
Right? And I'm not sure if I missed, did you show QA as well?
No. The plan is to run some QA. Partially the reason why not at this point is that the benchmarking sets that I've been interested in or the problems involved in those benchmarking sets are too big to run toy problems. Yeah.
So QA requires much more large circuits.
Yep. Yeah. But plan to run on some smaller instances, and maybe Priya has been doing that with the graph coloring. I'm not sure if she has, but yeah, for the biomolecular stuff, only like a tiny toy example could you run on QAOA. And I'm interested in the scaling analysis, and you can't really get that out on QAOA very well.
I believe we still want to run these.
Yep.
But I just want to say that as a kind of an outsider, I mean, I just think QAOA is too complicated to be useful.
Yeah.
You know, quantum is so simple, and in both of them are not guaranteed. Right?
Yeah.
So I can see that.
Yeah,
I mean, that's my, absolutely view.
Sure. Yeah. Yeah, it's been interesting sort of following the literature over the last few years, people saying QAOA can offer advantage. No, it can't. Yes, it can. No, it can't. Depending on the problem structure, it's perhaps possible. There's the one paper I cited a little bit earlier. I'm not as convinced personally by QAOA as I am by quantum annealing because the dynamics there are fully quantum. There's no back and forth between one chip and a classical optimizer. The more promising one to me seems to be, at least on near-term hardware, quantum imaginary time evolution. I don't know how much quantum imaginary time evolution is called. Yeah.
That's not good.
Yeah. So that's another one that I'd like to test this out with.
That sounds better.
Yeah. I think so. Less parameters involved, less going back and forth between classical and quantum chips.
On that topic, it's a side question. So your quantum really, was it purely quantum or do you have the hybrid solution?
It was purely quantum, and I chose to go that way just because it's easier to actually benchmark and the results are more convincing. You it's harder to tease out what the quantum contribution is if you are using a hybrid solver, especially because D-Wave's algorithm's proprietary in certain ways.
I was so curious about your general view and general opinion was on the no-freelance theorem. So, you know, there's one sense to look at this in order to say that you're going to apply this machinery on some other problem, or as well. But there's another one that says that maybe there's nothing in the no-freelance theorem that says that this can't be on average better. Right. That's cool. It's, I didn't know, like, depending on how you define it on the advantage, which is to describe this. Where do you see quantum methods being for optimization?
I didn't hear the last one.
What's sort of your viewpoint on where quantum computing is being its optimization problem at this point?
Sure.
The other reason that I ask is, as I understand it, when the optimization solvers classically in the industry, they basically don't care about the accuracy, they just care about the time to solution.
Yeah.
I didn't know, I was just curious what you were talking about.
Right, so multi-pronged question and a multi-pronged answer I will try to give. Right, so I'm not sure if you've seen this paper, came out, I believe last year, or maybe about 2024. And the authors show here that there should be an in-principle superpolynomial advantage for quantum combinatorial optimization versus classical when you're looking for approximate solutions, not exact solutions. Yeah, and I mean, for most problems, you're right that accuracy doesn't matter so much as have you got the solution. In computational biology, the energy of functions that you're working with are approximations anyway, so you don't want necessarily to find just the optimal solution to that function because it's an approximation. You want to sample many low energy solutions from that function and then go to the wet lab and see, okay, does this actually match reality? The no free lunch theorem part, at least as far as the encoding step goes, the approximate binary and the truncated binary solution, they only seem to work on particular flavors of cost function. If they're extremely random cost tables, then I don't expect them to work as well, or if there's a massively degenerate solution space. And Vikram, who's at Flatiron, he's working with a different benchmarking set that involves a very degenerate ground state solution space. And the results that we were seeing with protein design wasn't able to reproduce as well. Although, you know, one thing, again, within an optimization context is depending on how you map your variable choices onto these bit strings, you, within a classical context, really change the geometry of the solution space, but that doesn't matter in a quantum context as much. So you can take even random cost tables and rearrange them so that they become smoother. And then in those cases, you should probably see maybe not as good performance as in the case that your potentials are smooth to begin with, but improved versus just random assignments. Yeah.
How many higher order terms do you realistically really want to match? Because the second word of that first paper is doing a lot of looking at in principle.
Yeah.
It means that you might have to optimize possible. That I don't know that, but I'm betting that they're doing a computational proof, not necessarily something that they factor in the other issues. I imagine that for people who have more optimization time on top. But I'm wondering if, and one question is there a cost trade-off between how many high order terms you use, and the other question is how accurate is that.
Yeah, so not speaking so much about the in-principle stuff, but the more practical, forget where, hang on one second. I'm just gonna skip forward to this slide. Right, so in speaking about cost function networks in general, which are a very, very general class of combinatorial optimization problems, if you want to exactly preserve the energies present in the original cost function network, then the highest order term within a pairwise decomposable cost function network is equal to log 2 of di here, which is the number of choices within a given variable multiplied by 2. And if you have a very randomly structured cost function network to get good reproduction of the cost function under encoding, you need to include all those terms under random choice to bit string assignment. I haven't looked in detail yet at if you have a randomly structured cost table and you reorder the choices and then assign to bit strings. But there is this smoothness criterion. Where is it? Yeah, the smoothness criterion, where you can expect the basin itself to be preserved and the global optimum still remains global optimum.
So one of the big advantages of and if you have multiple problems, which most problems are in practice, then all of a sudden these near optimal solutions become very important, very useful, very handy to make trade-offs among the different variables. But first of all, no Hilbert is didn't talk about near optimal solutions. All of those solutions are part of
Why do they come in handy, near optimal solutions? Well, I did mention in the biomolecular context that comes in handy because the energy function that you're working with is an approximation to reality in the first place.
Yeah,
So
go to slide 39 at 50 years. The other one, yeah, that one. Yeah. So here you actually drop off some you can see the main parts, right? And if you go now to the 39. So for example, if you are arguing that to stay within the solutions are good, you always stay within the
basic.
yeah, block, right? So for example, take about that corner, get 1, 3, 4, these are the 5.
Yeah.
Here on the solution, I think those is that practical?
I think so, especially because the results I was showing previously, and none of these quantum optimization algorithms are guaranteed to find lowest energy solution. So really, you'd probably be sampling from here and be able to recover many of the solutions that do appear a little bit higher in energy than usual. So I expect that if you are interested in a diverse set of near optimal solutions, even carrying out this spectral truncation, you'd be sampling from those. It's definitely true of D-Wave that you're not sampling just the ground state solution, but a lot of low energy sided states as well.
So there were 2 papers by the during the thing from D-Wave. How do they relate to the sample?
So
right?
they didn't cut off anything, but they were working with natively quadratic optimization functions in general. In the case of the King paper, there were multiple optimization functions, and then in front of those was placed a weight determining how much are we trying to optimize this function versus this function versus this other function. A lot of true and practical problems involve higher order terms and more than binary variables. So I imagine that you could represent many different discrete variable, discrete domain, combinatorial optimization functions, and then weight them in exactly the same way. Using truncation like this or the approximate binary encoding and still be able to recover the Pareto front pretty well, but that's speculation and I can't say for sure.
So where your research is part about from the end to speed. But here, implementation, where we get the solutions, many times. Practically, it's not the speed that actually you actually get feasible solution from a whole bunch of what can be proposed. Is that something that actually
To be able to
on the ranch, not just speed.
I think about it more in terms of speed and maybe energy, like actual costs to achieve some objectives that you're looking for. And I mean objective in a more general sense.
The house is too much sense. You know,
I didn't ask you.
okay, so, but anyway, I just want to say that if you want to claim something, then you need to look comparison. So you need to express those words in a precise way and compare and quantize with.
Yes.
What, you know, and, but I'm just saying this because, you know.
Have you done it?
No,
Okay,
I haven't done it.
Okay. Well, Tristan, thank you.
Thanks, Jose.
Absolutely.